Hello everyone, welcome back. Today we are covering 7 data engineering concepts that every data engineer needs to know. These are the concepts that come up in interviews, in system design, in every production data platform. I'm not going to give you boring textbook definitions. I'm going to explain each one like I am talking to a friend over coffee. Let us get into it. First concept, change data capture. We call it CDC. Imagine you have a database with 100 million records. Every night, you copy the entire thing to your data warehouse, all 100 million rows, even though only 500 rows actually changed. That's insane, right? If you have only 500 records changed, like updated, deleted, inserted, and you need to load 100 million records every day to your data warehouse, including the history, etc. Right? What does that mean? That means you need a lot of power, a lot of resources, and it requires a lot of time to run and to copy 100 million records into data warehouse. What should we do in this situation? CDC fix this situation. Change data capture. So instead of copying everything, you only capture the changes, the inserts, updates, and deletes that happened since the last sync. Obviously, the first time that you run this job, you need to load all the data right into the data warehouse. But the second run, you don't need to load all the historical thing. You need to load only the new records, the ones that are updated, or if some of the records deleted, so you need also to reflect that in the data warehouse somehow. This kind of a process, the strategy to build this thing called CDC, change data capture. So that means you copy only the data that have been changed from the last run. So the most popular way to do this is log-based CDC, using tools like Debezium. Your database already keeps a transaction log, a record of every change. Right? So CDC tool read that log and stream only the changes in near real time. Instead of moving 100 million rows, you move only 500, the one that's been changed, for example, right? Faster, cheaper. That's how CDC works. Very easy concept. There is another way where you have a column there called like last update date, wherever in the database, and then you check based on that. But the most common one is the log base. This is the CDC, change data capture. Let's move to the next concept, which is Idempotency. The name looks complicated, but the concept is extremely easy. Let me explain. Imagine your pipeline crashed half through, okay? You restart it. Now you have duplicates, data everywhere because you restart the pipeline. You rerun it again, all right? Now dashboards show double the revenue, for example, which is a very big problem. Now what we do, this situation happened, you rerun your pipeline second time and the data doubled. What does that mean? That means your pipeline is not idempotent. Basically, an idempotent pipeline gives you the exact same result no matter how many times you run it. Run it once or run it 10 times, the same output. That's it. It's easy as it is. Basically, when you develop your pipeline, you need to handle this case and make sure if you run it multiple times, you still get the same data. Now you might wonder, okay, how I'm going to resolve this? There is different ways. For example, very common pattern include delete and replace. Before you execute a new run, you remove the existing ones and rerun it again. That's one. Like a partitioning. You don't need to remove all the history just for that particular day. Right, you kind of replace it. We also have the other one, which is called merge, where you compare the existing one and the one that's coming. And then if some of the records already exist there because of the first run that failed halfway, right, you don't need to replace that one. You just add the new one, for example. This is one way called merge, and the most popular one is delete and replace for that particular partition. All right. Now the rule is simple. Never assume your pipeline is running for the first time. Most of the time, things fail in production, right? And the concept is this. If rerunning creates duplicate, you have a problem. That's it. Now, before we keep going, if you are watching this and thinking, I want to become a data engineer, or I want to level up my career in data engineering, I have something for you, okay? I run a coaching program where I personally help you break into data engineering or go from junior to senior. We cover everything needed for you as a data engineer: SQL, Python, cloud, pipeline, system design, interview preparation, everything with real projects and one-on-one guidance. If that sounds like what you need, there is a link in the description to book a free call with me. We chat about where you are and how I can help. Of course, spots are limited, so grab one while they are open. All right, back to the concept. Now, concept number 3, Medallion Architecture. How do you organize data in your data warehouse? How do you go from raw, messy data to clean, business-ready tables? The answer most teams use is the Medallion architecture. It's very simple. Medallion architecture looks like this. We have 3 layers, okay? Bronze, silver, and gold. A bronze is raw. Basically, you dump data exactly as it arrives. JSON blobs, CSV files, raw API responses, no cleaning, okay? It's the same as it's the source. Now we move to the next layer, which is silver. Silver is a cleaned, meaning you parse the data, remove duplicates, fix types, handle nulls, etc. It is structured better than the bronze, but it still looks like the source system, right? That's the second layer. The third layer, which is gold, consider as business ready layer. That means you join tables, calculate metrics, build the final tables, dashboards use, revenue by region, for example, monthly active users, whatever the business needs. Now the beauty is if gold breaks, you rebuild from silver. If silver has issues, you go back to bronze. You never lose data. This is very common architecture. Now let's talk about concept number 4, slowly changing dimensions. This is extremely popular in data engineering space. The issue is this. You have a customer table, okay? One day a customer moves from London to Berlin. So the customer's address changed, right? Now the question is, do you override the old city or do you keep both? This decision is what slowly changing dimension is all about. Do you want to keep the history or do you want to get rid of the history, just get the latest update? What do you want? That's basically it. There is 2 types. We call slowly changing dimension type 1 and slowly changing dimension type 3. In fact, there is 3 types, but let's talk only about 2 types, which are the most common. First type is very simple, all right? You overwrite, but you lose the history, of course, forever. You will never know when this customer lived in London, right? You will see only Berlin. That's it. Because we already overwrite the old one. That's type 1. Some scenarios need only this, right? Not all scenarios requires to keep the history. Now type 2, you add a new row with the new city. And you add date to it, valid from, valid to, from to, these dates, you add them. This customer was living in London during this period, right? And for the next one, now you have full history, right? Because the new records will have Berlin, right? That's the new location. 5, which is the orchestration. Let's imagine that you have 50 pipelines. Pipeline A must finish before pipeline B. All right? C depends on both A and B. Now we have D runs every hour. E only runs on weekends. How do you manage this without losing your mind? Now you need to orchestrate, right? That's the answer. An orchestrator like Airflow, which is the most popular tool to orchestrate your pipeline. We have different tools as well, like Dagster or Prefect. These tools does 4 things. The first one, it defines dependencies. It says run B only after A succeeds. The second one, it schedules runs. You'll be able to schedule this task, okay, for example, 2 a.m., 3 a.m., hourly, daily, monthly, weekly, etc. The third one, it handles failures, retries, alerts, and prevent downstream tasks from running with bad data. And the last one gives you visibility, like a dashboard showing what ran, what failed, how long it took. Without orchestration, you end up with a mess of cron jobs and scripts nobody understands. With orchestration, you have one place that controls everything, which is a great solution. Let's talk about concept number 6, which is data contracts. Here is the situation. Imagine the situation. The upstream team renames a column without telling you. If you don't know what I mean when I say upstream, basically upstream, the people that producing the data, right? Downstream are the consumers. If I have a team consume my data, they are my downstream team, right? And that's what we mean when we say upstream team or downstream. So if my upstream team renamed a column without telling me, what would happen? Because I'm reading from these data sources, right? And I designed my pipeline to read this particular table, for example, and now I don't see that column because the name changed. Now the pipeline will break. So we spend many hours debugging. This is a very common issue. Data contracts exist to prevent this situation. Basically, a data contract is a formal agreement between the team producing data and the team consuming it. It defines exactly what the data looks like. Columns, data type, formats, update frequency, quality expectation, everything. Now you have a contract there, so you make sure you don't publish or you don't send the data to your downstream models until you align with the contract. That actually prevents you from pushing the data into your downstream models. Now we have a system, right? If the producing team upstream wants to make a breaking change, the contract forces them to communicate first. It will fail. It will not allow them to send us the data. It will say, okay, you have change in the name of the data type. For example, tools like dbt test and models, you can define AML models in dbt test and enforce the contract. Helps a lot. And if a role is violated, the pipeline catches that before bad data hits dashboard. That's the concept basically. Now, let's talk about the last one, which is data observability. Imagine this, your pipeline runs successfully, okay? Green check marks everywhere, looks perfect. But the output numbers are completely wrong. Now, the pipeline did not fail, right? It silently produced garbage. This is the nightmare data observability solves. Let me explain. Observability monitors the health of your data, not just whether pipelines run or not. It tracks 5 things. The first one, freshness. Is data arriving on time? The second one, volume. Are we getting the expected row counts? The third one, schema. Did columns change unexpectedly? And fourth one, distribution. Are values within normal ranges? And last one, lineage. Where did this data come from? For example, if your daily table usually has 50,000 rows and today it has 500, observability catches that immediately, even though the pipeline technically succeeded, right? The shift is from reactive to proactive. Instead of waiting for someone to say, this number looks wrong, you catch problems before anyone notices. And those are 7 concepts every data engineer needs to know. If you made it this far, you now have a solid understanding of some of the most important building blocks in data engineering. If you found this helpful, hit that like button and subscribe. Drop a comment below and tell me which concept was your favorite or which one was new to you. Remember, if you want to become a data engineer or level up your career, the link to book a free call with me is in the description. I would love to help you get there. See you in the next one.